I'm from the mathematics group here. So today I'll be talking about reduced descriptions of chemical rate processes using column selection. So just to motivate this research, even though this research actually yields some very general mathematics, we can note that understanding chemical kinetics problems is a bottleneck to many applications. So anytime you want to analyze or design any kind of biomolecule or chemical system, you have to understand chemical kinetics, and doing so can be extremely difficult. So a few application areas that I have in mind are the field of DNA and RNA secondary structures, competing enzymatic pathways, and then for a more physics-based model, magnetization, and a classical spin lattice. So the problem with most realistic chemical systems is that they tend to be vast and complicated. And so to face up to this, we've developed a principled method for Markov chain reduction, which is using a few concepts, which are variance minimization, randomized approximation, and column selection. So to get started, the key problem in a lot of these chemical systems is that there are too many configurations and dynamics to possibly comprehend. And so our goal would be to capture the most information about some given rate process in the least output with minimal cost in the algorithm. And so we're trying to reduce an incredibly complicated kinetic system like the one shown on the left to a very reduced description with some theoretical guarantees. And so our recipes go to involve a few steps. First, we'll perform a principled reduction via marked process theory. Second, we'll pose an information maximization problem analytically using an isomorphism with Gaussian processes. And then algorithmically, we'll efficiently choose the states of our column selection via an iterative randomized algorithm. So in terms of the raw mathematics of what we're dealing with, we essentially have a weighted graph Laplacian, like the type that has been discussed in a few other talks here. And so we have some vast graph, which is some discrete space, finite but extremely large, where each of the nodes in the graph is some structure that a chemical system can adopt. And then every edge in that graph is an elementary transition that could take place as we watch this Markov process evolve. So to ground our approach of column selection, I'm going to introduce something called the marked chain, which is pretty simple to think about. So if we look at our Markov process can be realized as a stochastic trajectory, like shown in blue. So we watch our process, and we pay attention to what structure it is at every point in time. And so we can watch every structure that's visited as is labeled in the top graph. But throwing out all information about all columns except for a few given states would yield something like the bottom trajectory. So this is the same process, but just only paying attention to when the process visits a subset of a few states. So nicely, we can derive a reduced Markov process, even though the bottom timeline or bottom trajectory is not perfectly Markovian. We can derive a reduced Markov process using the discrete Green's function of the top process. And so this gives basically the most likely reduced chain that would yield the observed sequence and intervals of our original trajectory. So that sort of grounds how we can think about column selection applying to this problem. But a key problem is what makes a subset of states good. So how do we actually choose the columns in our approach? And for this, there's a variety of ways to think about it, but I guess my preferred way is to think about the following isomorphism with Gaussian processes. So it's known theoretically that the inverse of a Laplacian is going to give you the covariance of local times in an infinite time limit of that process. And so to every reversible Markov process, we can define an equivalent Gaussian process with a covariance kernel. And once we have that kind of probabilistic model in place, we can use the concept of variance reduction to guide which states are chosen. So stepping away from kinetics for a minute, now that I'm introducing a Gaussian process, we can think about what basis to choose for that process. So a good basis is basically one that should minimize the average conditional variance of local times over all of the states. And so this is basically mathematically analogous to a sensor placement problem. So if you imagine that you had a space with some unknown temperature profile, you could think about what's the set of thermometer locations in which I should place thermometers to minimize the average uncertainty and temperature over the complete space. And so we can phrase this very neatly using the covariance function of the process, which is mathematically tractable. But unfortunately for our graph Laplacian, one, enumeration of all of the subsets of the state space is completely infeasible. And then not only this, but some of the matrices in this recipe are actually very difficult to compute or store. And so algorithmically, we've developed a greedy approximation algorithm to avoid exhaustively testing all of these subsets. And so essentially what that means is that we can choose one column at a time by maximizing the following ratio. And interestingly, we can actually theoretically bound the performance of that pretty rigorously, and it's not too far from optimal. Meanwhile, since we don't actually have access to the matrix G in this expression, we can approximate it via randomized trace estimation, where we're drawing vectors from uniform Gaussians and then solving for the inverse Laplacian values with existing preconditioners that are developed for graph Laplacians. So how does this work in practice? I can go through a couple of relay toy problems. So in one-dimensional system, we might have a two-well system where there's a probability density on the left and the right side. And unsurprisingly, our algorithm would select columns to represent the left and right sides as separate macrostates. We can get a little bit more advanced by going into a five-well system like the one shown on the bottom. And again, we obtain exactly what we would expect for the chosen subset of columns. We can move on to a realistic scenario. So here, I'm performing an automatic analysis of an example RNA folding landscape. So here we have more than 20,000 states in a pretty large graph Laplacian. And the approach basically gives a set of four macrostates that are depicted on the top with some reduced kinetics between them. If we then propagate our reduced Markov chain versus the original Markov chain, we can see here that it's almost quantitatively exact, so the error is basically negligible. And so I hope this persuades you that our kind of model reduction is both scalable and accurate. So with that, I'll conclude. So I hope I've shown that reversible Markov processes can be reduced using principal column selection of the kind that I've described. I hope I've motivated that the problem of optimal column selection or optimal macrostate decomposition can be posed using a Gaussian process isomorphism. And then finally, we've actually developed a pretty performant and iterative randomized algorithm with theoretical guarantees that can output macrostates which are close to optimal. So thank you.